Hello and welcome to Chapter 10. We have finished integrals, so we're going to move on to sequences and series, which is Chapter 10. And in order to talk about series, we have to first talk about a sequence. A series is just going to be a certain operation that we do on sequences. So let's nail down sequences first. So, definition. What is a sequence? A sequence is a list of numbers written in a specific order. We index the sequence with positive integers. So, for example, we could have A1, A2, A3, comma, dot, 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 comma, AN, comma, dot, dot, dot. So this would be the first element in the sequence, the second one, the third one, the nth one, and it just keeps going. A nice way to view a sequence is as a function but we restrict the domain to only positive integers. The positive integers are infinite, they just keep going. So we need to talk about infinite sequences, and we will denote an infinite sequence as a curly bracket, an, curly bracket, and then we do from n equals 1 to infinity. So example, we could talk about the sequence n over n plus 1, starting from 1, going up to infinity. This sequence, the first element in the sequence is a 1, which would just be replace the n in your an with 1. So replace anywhere you see an n with 1, and that would be 1 over 1 plus 1, which is 1/2. The second term would be replace every instance of n with 2, so that would be 2 over 2 plus 1, which is 2/3. And the third term in the sequence would be replace every n with a 3, so that would be 3 over 3 plus 1, which is 3/4, and etc. It keeps going. Second example of a sequence, we have curly bracket, we have negative 1 to the n times n plus 1 divided by 3 to the n. And we'd start at 1 and go up to infinity. So the first term in this sequence would be replacing n with 1. So it'd be negative 1 to the first times 1 plus 1, which is 2, divided by 3 to the first, which is 3. A2 would be negative 1 squared, which is just positive 1. And then you have 3 divided by 3 cubed, which is 27. Sorry, we're on 2. 3 squared, which is 9. So that would just be 1/3. And then one more, A3 would be negative 4 divided by 3 to the 4th. So nice thing to note here is we see that the terms in the sequence alternate between negative and positive. And they're just going to keep alternating. And that is coming from this negative 1 to the n. So anytime you see a negative 1 to the n, just immediately think it's going to alternate between positive and negative. So some definitions involving sequences. The infinite sequence, an, This sequence converges to the number L if the limit as n goes to infinity of an equals L. If no such limit exists, then we say that the sequence an diverges. So this is very similar to the improper integrals. That's why we did the improper integrals last in our sequence, in our integral techniques. In that an infinite sequence converges if, as you go off to infinity, if that tail goes to something. And then if it doesn't, then it diverges. So how would we visualize a sequence? So let's plot the sequence 1 over n from n equals 1 to infinity in R2. So on just your normal coordinate system. So if we were to do that, we would have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3. Let's not do that. 1, 1/2, 1/4. So when n equals 1, which is going to be our x-axis, an is also 1. So our y-axis is an. When n equals 2, we then have 1/2. When n equals 3, we have 1/3, just like right there. When n is 4, we have 1/4, then 1/5, then 1/6, then 1/7. So this is what our sequence looks like. And this looks like the function 1 over x. And it looks like it tends to 0. And that is as n goes to infinity. So the fact that this looks like 1 over x and it's behaving like 1 over x means that we can use our knowledge of functions to deal with some aspects of sequences. So we have a theorem. This is the continuous function theorem. This is one way that we can use information from our function to tell us information about our sequence. So if the limit as x goes to infinity of f of x, our function, equals L, and if f of n equals our sequence an for all positive integers, then we know that the limit as n goes to infinity of our sequence has to equal L. So what is this really saying? This is saying that if we know the end behavior of a function, and that function agrees with the sequence wherever it should, so on the positive integers, then we know the end behavior of our sequence. In other words, we know what it converges to. So there are some limit rules for sequences. These are really the same as those for functions, but we're just going to reiterate them here because we'll be using them a lot. So let the limit as n go to infinity of an equal L, and let the limit as n goes to infinity of bn, another sequence, equal n. Then we have the sum rule. That is the limit of the sum equals the sum of the limits. So that would equal L plus M. We have the constant rule. And that is the limit of a constant is just a constant. We have the product rule. That is the limit as n goes to infinity of an times bn, just is L times M. We also have the quotient rule, which is similar to the product rule. The limit as n goes to infinity of the ratio an divided by bn is just L divided by M. You can bring the limit inside of the ratio. And last, we have the power rule. The limit as n goes to infinity of an raised to the p equals L to the p. So you can take the limit of the base and then raise it to the p power. And this is assuming only that an is positive and p is positive. Can't always do this if the base an is not positive. So our goal is to find the limits of sequences. So we're going to state some theorems to help find these limits. Okay, so the first one is the squeeze theorem. Now you probably saw this in Calc 1. If not, that's fine. Okay, so let the sequence an and the sequence bn and the sequence, should really have commas instead of that and the sequence cn be sequences satisfying an is less than or equal to bn is less than or equal to cn for each little n bigger than or equal to capital N for some positive integer capital N. So this is saying that each term an is less than bn is less than cn. That is what this for each n, and that is each term past some point. We don't care what it does in the beginning because the limit or the convergence or divergence only cares about the tail end. So we don't care about what happens at the beginning. We care that at some point we can say that this inequality holds for every point after that one point. That one point would be capital N. Then the statement of the squeeze theorem is if the limit as n goes to infinity of an equals the limit as n goes to infinity of cn, and both of these are L, then the limit as n goes to infinity of bn has to equal L also. The fact that bn satisfies this inequality, it's being sandwiched or squeezed between an and cn, and an and cn are both approaching the same number, well then b has to also approach that number. It's stuck between the two. Okay, next theorem. We have if the limit as n goes to infinity of the absolute value of an equals 0, then you can drop the absolute value, the limit as n goes to infinity of an equals 0. And note, this is only true if the limit equals 0. This would not be true if the limit equaled 1 or any other value. It has to be 0. So examples. What do the following converge to? Part A, we have this sequence n over n plus 1. So to figure out what this sequence converges to, we just take the limit. So this is the limit as n goes to infinity of n divided by n plus 1, which is 1. We look at the largest power in the numerator, which is n, and the largest power in the denominator, and then compare coefficients, since they are the same power. So that means that this sequence converges to 1. Part B, we have the sequence natural log of n divided by n. Okay. So with this one, looking at this, we want to take the limit as n goes to infinity of natural log of n divided by n. But we can't do that. We don't know how to take this limit. But if instead we let f of x equal the natural log of x divided by x, then we have that f of n would equal an for each, for positive integers n. So we have a function that behaves exactly the same as our sequence, and we can take the limit of this function. We couldn't take the limit of this function because we're only dealing with integers, but here f of x we can deal with all real numbers. So when we take this limit, this is the limit as n goes to infinity of the natural log of n divided by n, is the limit as n goes to infinity of the natural log of x divided by x. The natural log of x, when you take this limit, you get infinity over infinity, so you have to use L'Hopital's rule. L'Hopital's rule says, and I messed up, these n's should be x's because we switched variables. L'Hopital's rule says that you take the derivative of the top and the derivative of the bottom. So we have 1 over x and 1, and that is just 0. Therefore, this sequence converges to 0. Okay, part C, we have the sequence cosine n divided by n. Oh no, I grabbed too much. Okay, solution. We can't take this limit also because this cosine n is oscillating between -1 and 1. But, as I just said, we know that cosine n oscillates between -1 and 1. So if you divide everything by n, you have 1 over n is less than or equal to cosine n divided by n is less than 1 over n. And the limit, as n goes to infinity, of -1 over n equals the limit as n goes to infinity of 1 over n equals 0. So we have cosine n over n squeezed between -1 over n and 1 over n, both of which go to 0. So the squeeze theorem tells us that the limit as n goes to infinity of cosine n divided by n is also 0. And D, we have the sequence -1 to the n divided by n. Again, we cannot take this limit because this is oscillating between -1 and 1. So looking at this, you can take the limit, but the way we will do this is we'll make use of the theorem that was mentioned after the squeeze theorem. We look at the limit as n goes to infinity of the absolute value of -1 to the n, which is just the limit as n goes to infinity of 1 over n, which is 0. So the theorem after the squeeze theorem tells us that the limit as n goes to infinity of our sequence without the absolute value must also go to 0. And again, this is only because it is going to 0. If this instead went to 1, then what we could say is, well, if n is even and we go along only even values, then our sequence converges to 1. But if we go along negative values, then the -1 to the n will always be, not negative, odd values of n. If we go along odd values of n, then this -1 to the n will always be odd, always be negative. Getting my odds and negatives mixed up. Which means that this would go to -1 if this went to 1 instead of 0. So it's the fact that 0 is neither positive nor negative. Or in other words, -0 equals 0. So you just don't ever talk about -0. That you can take the absolute value and then say, oh, we can take away the absolute value then. I have a homework problem that goes into more detail on this. So we've only looked at sequences that converge, so let's look at some sequences that diverge. So the following sequences diverge. We have the sequence -1 to the n. And this diverges because the limit as n goes to infinity of the absolute value of -1 to the n does not equal 0. In other words, exactly what I was saying before, go along even values of n, you get 1. Go along odd values of n, you get -1. Those don't agree, so this does not converge. We also have the sequence -1 to the n times n. This does not converge because of the limit as n goes to infinity of the absolute value of -1 to the n times n equals infinity. So even if you dropped the -1 to the n, this wouldn't converge. And then we also have the sequence sin n. This continuously oscillates between -1 and 1. So the main reason we talk about, in my opinion, the main reason we talk about series is to talk about Taylor series. And in Taylor series, we will need to talk about the factorial. So let's talk about it here. The product of the first n positive integers so as n times n minus 1 times n minus 2 times ... times 2 times 1. This is denoted n factorial, and as I said, it is called n factorial. I have too many things there. Factorial. Convention, we define 0 factorial, the product of the first 0 positive integers, to just be 1. There's a combinatorial reason for this. Factorial is going to be the number of ways that you arrange n people in a line. And if you have no people in the line, And there's only one way to have that, and that's have an empty line. And that's where we get the 1 from. So example, we can find the limit of the sequence n factorial divided by n to the n. So this one's going to be a little bit harder because we haven't talked about how to find the limit of an n factorial, or n to the n. So we're going to have to do something a little bit different than just trying to take this limit. So let's investigate a little bit. The first term would be 1 factorial divided by 1 to the first, which is 1. The second term would be 2 factorial divided by 2 squared, which is 2 divided by 4, which is 1/2. The third term would be 3 factorial divided by 3 to the third, which is 3 times 2 times 1 divided by 3 times 3 times 3. That is 6 divided by 27. Cool, not very helpful. But when we write it this way, we see that we can block it off and get 1 fraction, 2 fractions, and then a third fraction. So in particular, combining the first 2 fractions, we see that this is less than or equal to 1, and then we're just left with the third fraction. So this all together is less than or equal to 1 times 1/3, which is 1/3. And notice what we have that the first term is less than or equal to, it's actually equal to 1 divided by 1. The second term is less than or equal to 1 divided by 2. Third term is less than or equal to 1 divided by 3. So we suspect that the nth term, which is n factorial over n to the n, we suspect that this will be less than or equal to 1 over n. So let's see if we can get that. Well, n factorial is n times n minus 1 times n minus 2 times 2 times 1. N to the n is n times n times n times times n times n. And then we do the same thing we did with 3. We make a whole bunch of fractions, n fractions. And then we see that the first fraction is 1. The second fraction is something smaller than n divided by n, which is less than 1. The next one is also less than 1. All the way down to the second to last one is less than 1. And then the last one we're just going to leave as 1 over n. So we have this fraction, whole fraction, an. The first n minus 1 parts of the fraction are less than or equal to 1 times the last part, which is 1 over n. Well, this is good because we have now n factorial will always be positive, n to the n will always be positive because we're only looking at positive integers for n. So we have 0 is less than or equal to an, which is less than or equal to 1 over n. So we can use the squeeze theorem since 1 over n goes to 0. So why was this an important example? First off, it showed you a unique way of looking at this factorial and n to the n. Breaking up the n factorial as looking at like the different terms will be common in the future sections. But the other reason this is important is looking at an. It's a very common thing to say, and I will even say this, that n factorial is the fastest growing thing that we know. What does that mean? That means that if you have a limit and you have a factorial in the limit, then the factorial will probably dominate, and that's just the only thing you should look at. But here we have an example of, look, n to the n actually grows faster than n factorial. It grows faster, so the bottom grows larger. It goes, this is basically 1 over n, as we said. Therefore, n to the n grows faster than n factorial. So n factorial does grow faster than most things, but we already found one thing it doesn't grow faster than. Okay. We're going to do a few definitions. And then one more example. So, definition. If the sequence an, not is, I messed that up. Let's get rid of an. If, I was right the first time. If a sequence an, got lost in my notes, is bounded above and below, then we say that it is bounded in general. So what does this mean? This means, i.e., there is a number m such that the absolute value of an is less than or equal to m for all n positive integers. If it's not bounded, we call it unbounded. Note, every convergent sequence is bounded. If it converges, that means that it goes off to a number instead of going off to infinity. So it goes off to a number, let m be that number for the most part, and then it's bounded by that number. Whether that's bounded below or above, it is bounded. However, not every bounded sequence converges. So you can think about the sequence an equaling negative 1 to the n. This sequence does not converge, we already talked about that, but it is bounded. This is only ever 1 or negative 1, so it is bounded by 2. This function will never get larger than 2. So some more definitions. The goal then, if we have every convergent sequence is bounded, but we have the converse is not true, every bounded sequence does not converge, what other requirements do we need to put on bounded sequences in order for them to converge? So a sequence, an, is non-decreasing if an is less than or equal to an plus 1 for all n. So that is just saying that at no point does it ever decrease. And we have something similar, so likewise for non-increasing. So if it is always just going down, never does it go up. So sine x is not non-decreasing or non-increasing because it goes up to 1, then down to negative 1, then back up to 1. So at some point it increases and at some point it decreases. Such sequences are called monotonic. Okay, why is that important? Well, we wanted the converse of all convergent sequences are bounded, and that converse is the monotone convergence theorem. Monotone convergence theorem says every bounded monotonic sequence converges. So, an example. Show that the sequence AN equals 1 times 3 times 5 times ... times 2n minus 1. So all odd numbers in the numerator that are less than or equal to n, divided by 2 times 4 times 6 times ... times 2n. So divided by all even numbers less than or equal to 2n. Show that this sequence converges. So we cannot take the limit of this. This is it's a very weird sequence compared to what we've seen. It's not really a polynomial, so limits don't behave very well. So instead we're going to use the monotone convergence theorem. So to use it, we need to show that this function is bounded and is monotonic. So notice that an is just 2n minus 1 divided by 2n times an minus 1. We can recursively define this sequence where if you want to get to the next term, you just multiply this by this extra 2n minus 1 times over 2n term. Since 2n minus 1 divided by 2n is less than 1 for all n, we have an is less than an minus 1. So this is a monotone sequence. Monotonic, sorry. And by that we mean it's never increasing, so non-increasing. Okay, so it's a monotonic sequence, so now we need to show that it's bounded. So also note that an, if we write this out, we can, as we did in a previous example, look at each fraction. So group the first term in the numerator and denominator, and the second term in the numerator and denominator, all the way to the last term in the numerator and the denominator. Okay, this is less than or equal to 1/2 is less than 1, 3/4 is less than 1, 5/6 is less than 1, and 2n minus 1 divided by 2n is less than 1. So each one of these terms is less than 1, so we know that an is always going to be less than 1. So this sequence is also bounded. Then, by the monotone convergence theorem, our sequence an must converge. And that finishes section 10.1. We looked at sequences and we looked at when do they converge and diverge.